Thank you for joining us today. I will share my screen to give you a few words about Society of Piping Engineers and Designers. So welcome everybody. This is Society of Piping Engineers and Designers. Our society is an international non-profit organization promoting excellence and quality in piping design and engineering through networking, training, and certification programs. It all began when a four-year engineering technology program in process and piping design was started in the fall of 1977 at the University of Houston. It's founded and established in 1980. We have now members from the globe around the world. Plus, we have 34 corporate membership. Egypt chapter has been founded January 2019. Currently, we have members from Egypt, Algeria, Saudi Arabia, and United Arab Emirates. And this is our contact information. Membership is good for all participants. It gives you a good experience. It makes an exposure to piping engineering and design skills. It gives you an exclusive access to different technical materials and methodology of development and many other benefits which you can gain after getting our membership. We have 4 levels of certification, started from level 1 to level 4. That's all. I know the subject of stress analysis is very exciting for all of us. And we have to ask now Dr. Alex to start giving us what we are very exciting to know about. Thank you.
Okay. Thank you everybody for joining us. My name is Alex Matveev and I am developer of the pipe stress analysis software that is widely used in Russia. It is StarProf, and today I will tell you some words about pipe stress analysis and show some live cases in this software. So what is the pipe stress analysis? The pipe stress analysis involves examining of the flexibility of stress critical piping systems under different loading conditions and the results of the pipe stress analysis that you can receive. It is the stresses in pipes and fittings, stresses in insulation, stresses in flows, cracks, and other defects, displacements, the forces and moments at restraints and equipment, longitudinal buckling check under external pressure, flange leakage check, expansion joint deformations, and spring hangers and support selection, and natural frequencies of the piping systems. So all of these are available as results of stress analysis in StarProf software. The loads on piping system divides on 3 categories. It's primary loads that include internal pressure, weight of the pipe, piping component, insulation, fluid weight. The secondary loads, it's pipe thermal expansion and contraction. And occasional loads, it is wind, snow, ice, seismic, discharge reaction loads from relief valve, PSV, slug flow loads, water hammer loads, and other. And when do we need the pipe stress analysis? Some codes have the rules when we need to perform pipe stress analysis. Some industries and companies use own guidelines. And here are the common rules. I will not read this. I think you can just see it on your screen. and it is not required then exactly the same piping has been previously analyzed and operated successfully for many years, for example. First of all, we need to select the wall thickness of the piping system. StarProf software allows you to select the wall thickness of the pipes and other components. You just type the properties of the pipe and receive the wall thickness, or you can type the wall thickness and receive the maximum allowed pressure for this component. Here you can see the equations according to different piping codes, how the wall thickness is calculated. This is wall thickness calculation for the band, pipe band elements and meter band elements. You will be able to download this presentation in a PDF format from our website, pessuite.com, in the resources section of the StarProf software. And also, we will upload this video on our YouTube channel. It's youtube.com/pessuite. We need to calculate the sustained stresses according to the various codes, according to the following equations that you see on the screen. This is the allowable sustained stresses according to different piping codes. Also, we need to calculate the occasional stresses from the wind loads, for example, seismic loads and other type of occasional loads. And we need to check also the stresses in the test loading conditions. Also, we need to check the expansion stresses according to various codes. This is the expansion stresses according to some codes that is implemented in StarProf software, and the allowable expansion stresses. So why the expansion stress check is important? Because the low cycle fatigue leads to failure of the piping components, especially the bands and tees, after several years of operating, and the explosion can happen because of the cyclic loads, the thermal expansion and contraction, when you heat up the piping system and cool it down. Also, the buckling check is important because sometimes our piping can buckle. Especially the buckling is important if it caused by the primary loads, the weight and the pressure expansion. But it is also should be checked from the thermal expansions, because we can receive the problems with flange connections, with supports, and with low cycle fatigue of piping and supports that can be caused by the buckling, longitudinal buckling of the piping. Here you can see the results. You can check the longitudinal buckling using StarProf software. This is the upheaval buckling. You can see the importance of checking upheaval buckling. Also, StarProf allows you to check this problem and avoid upheaval buckling in your pipeline system. Also, it is important to check the vacuum piping under external pressure. StarProf allows to check you the piping system from the external pressure. Also, here you can see the result of buckling of steam piping system under the external pressure. Also, here you can see how important to check the displacements of the piping system. because if you will have great displacements of the supports, the piping can fall out from the supports. And also it is important to check the equipment loads and support loads, because support and equipment nozzle may fail under the extreme loads. And also we need to check the expansion joint deformations. Here you can see the result of exceed of allowable expansion joint deformation. A quick description of StarProf software. It was developed in 1965. At this moment we have 3,000 users. We have a user interface in English, Chinese, and Russian languages. We have 32 piping codes and 18 wind, seismic, snow, and ice codes. The user interface is object-oriented, so you work with piping system like with objects, like in 3D modeling software. It is very easy. You can copy any object, delete object, and do everything you want. So we have pipe, rigid element, cylindrical shell element. Also, we have several equipment elements. It is a vessel nozzle that allows you to consider the flexibilities of the nozzle, check the allowable loads. Also, we have a tank nozzle that allows to consider the tank subsidence, bulging effect, tank allowable loads, and consider the flexibilities of the tank nozzle. Also, we have several pump nozzle elements that allows you to check pumps. Also inline pump element. We have turbine object, compressor object, and air cooler and fire heater. And we will add more objects in the future versions. We have several types of the band element, including the long radius band element that is used in pipelines, and including the meter joint and non-standard bands. Also, we have several types of T elements, reducers, and several support, predefined support elements. And also you can create your own support using the non-standard restraint. One non-standard support contains several restraints, and you can copy it like the one object. Also, we have several predefined types of expansion joint and expansion joint database, including the slip joint, with where you can define the friction force, and it will be automatically modeled. We have angular torsion element. It looks like flange connection, and we have ball joint element with friction moment. Also, you can define the cold spring and support movements. It's very easy. Just add this element into any support, and your support will move in any direction that you will specify here. And we have flow elements that allows to define the cracks or on the pipe and check the stresses in this crack. And we have databases. It's material database, spring database, constant spring database, soil, insulation, expansion joint database, the pipes and piping components, and insulation jackets. Some of the features of the software that we can calculate the occasional allowable stresses according to special part of the ASME B31.3 code for elevated temperature fluid service and appendix V. Also, we can calculate the Creep-rupture usage factor according to appendix V of ASME B31.3 code. The database already contains all the needed information for this check. Also, we can calculate the minimum design metal temperature, And StarProf also take into account the reduction of the lowest temperature according to the stress ratio between calculated stresses and allowable stress. It is done automatically. Also, StarProf can calculate the stress range not only between the installation state and operation state, but also between operation state and cold state. The cold state is the state of the piping system when it's cooling down from the hot state. When the piping system cooling down from the hot state, the friction forces change their direction. So the stress range between cold and operation state is greater than the stress range between installation state and operation state. But this stress range is traditionally used by most of the international companies, but it is not correct because the greatest stress range is between cold state and operation state. Also, StarProf can check the stresses in the piping system, in the high temperature piping system, and consider the creep effect. And the most important is the stress relaxation after cooling down of your piping system, because the special effect happening in this case, it is cold spring in cold condition of high temperature piping. It is this cold spring is caused by creep effect, and the ASME B31.3 code require to take into account this effect. But as I know, a lot of international companies doesn't model it, but StarProf software allows you to do this, and also you can receive the stresses in the cold condition after relaxation, and also you can receive the restrained loads in the cold condition. And usually the restrained loads and stresses in cold condition of high temperature piping is much greater than the stresses and support loads in hot condition. Also, StarProf can perform analysis of buried piping system, underground piping system, for the seismic wave propagation in the soil. It is longitudinal wave, shear wave, low wave, and relay wave. StarProf automatically perform this analysis. And StarProf can calculate the soil drop, soil subsidence, the soil fault, for example, seismic fault. Also, we can analyze the landslide effect. And also, StarProf can check the stresses in the insulation joint, also called insulation kit of the pipelines. Here you can see the codes that StarProf include for ice loads, wind loads, and also we have seismic loads. Here you can see the database for the constant effort hangers and supports. StarProf can automatically select the constant effort hangers and supports. And we have integration with Autodesk Revit and integration with Aviva, PDMS, and Everything 3D. This integration is two-way, so you can import the model and export some data back to the Everything 3D or PDMS. Here you can see the international codes that is included in StarProf. It is all ASME codes, European code, code of Canada, UK, plastic piping code, and fiberglass piping, all Chinese codes, and 11 Russian codes for all industries. Also, you can see here the wind, snow, and ice codes. The codes for equipment connection analysis, it is API for different type of pumps, tanks, nozzles, turbine, and compressors. And for flange check, here you can see the stress analysis features that is included into the software. And here you can see the CAD interfaces between StarProf and other 3D modeling software. And the benefits of StarProf at a very affordable price. Here you can see the price for permanent lessons that it will work forever, and annual lessons that works only 1 year, and technical support is included into the first year for free. Now I will show you live demonstration of the StarProf. This is the StarProf user interface. So let me create the new file. I will choose piping. I will choose ASME B31.3. It is most popular code. Here you can choose, for example, using of ASME B31J. You don't need to use any side software, so you can just check this checkbox, and automatically all T's, all reducers will be calculated following the rules of ASME B31J. StarProf will take into account the stress intensification factors and flexibilities of every T, every band, every reducer according to this code. So it's very easy and you can do this very quickly. And also we have several other options. I will not explain everything. Usually we do this during the training of StarProf software. So I will just click OK. And let me create some simple piping system. We have a database of the pipes, but I will not use it at this time. I will just type it manually. So let me create the pipe element 1 meter by Y direction. I will choose the material, this one. You can define pressure, define temperature, and you can define the fluid weight. For example, it will be water. Also, some codes has the additional properties. For example, here you can specify the Y factor used for pressure analysis and well-joint efficiency factor. Okay. The first pipe is created. I will add here the anchor. Now I will create the vertical pipe. All properties already taken from the previous pipe, so I will just type the length of this pipe by Y direction and add the next pipe like this in minus X direction. Oh, sorry, minus Y. No, I need minus X. Okay. Oh, sorry, plus X. Now we can add the band elements. We have several band elements. I will just use this one. It will be long element. You can define any properties of this band, but by default, all the properties is taken from the connected pipes. Now we can copy this band into a clipboard and paste here. Now I will copy the model into a clipboard, and after that I will paste. Oh, no, sorry. I will perform mirror function. Mirror. The plane will be ZOY. This one. Okay. So this piping is copied. Now I will add the vertical pipe here For example, it will be 4 meters. And also I can add the T element here. It will be a welding T. Also, you can define the length and height of the T. In this case, StarProf will take into account the increased wall thickness of the T, but I will not use it right now. Usually we use this option for Russian codes, but for ASME codes it is not necessary. Okay, now I will define the -y element and copy the band using Ctrl-C and Ctrl-V combination. And in this point, I can model the nozzle. For example, I will put here the nozzle element. Okay, I will choose the material, the temperature. Okay, so now you can define the vessel diameter. You can define the length of the vessel. For example, it will be 2 meters. At this moment, I will not take into account the vessel flexibility and allowable loads. So our model is ready. I will save it. And we're ready to run analysis. Analysis is done. So now we can check the deformed shape. It looks like this. You can check the stresses. Everything is okay here. And also we can check the stresses in the model. I choose output piping stress. You can see the sustained stresses, its primary stresses, alternative and standard sustained stresses according to the ASME B31.3 code requirements. You can put your mouse over any cell and see detailed report with all the calculation data. If you want to check how does StarProf calculate and how did this value was calculated, you just put your mouse over any cell and see detailed report. Here is the allowable stresses, and here you can see the expansion stress calculation and allowable stress range, expansion stress range. Okay, the same, you can select the restraint loads. You can see restraint loads in operating case, in cold case, and nozzle equipment loads. You can see the equipment loads, but I didn't define any allowable loads, so we don't have allowable loads here. Now I can define allowable loads. For example, I can define it manually. I will just add 1 kilogram. And also I can take into account the nozzle flexibility. To do this, I need to click here and define the property of the shell element. It will be diameter, wall thickness, nozzle wall thickness, nozzle diameter, nozzle wall thickness, the shell length, for example, 4 meters, and offset it will be 0 from the middle point. Now click OK. Here you can see the flexibilities of this nozzle, and here is allowable loads. I click OK, run analysis, and see restraint loads, and you can see the equipment loads. Now you can see that allowable loads is 1 kilogram because I type only 1 kilogram, and you can see red cells. That means that this load didn't pass the strength requirement. And also, if you open the animation of deformed shape, you will see the nozzle flexibility. Here you can see that nozzle rotates around the x-axis. Okay. So now also you can toggle the WRC code stress check and run analysis again. And you will see the stress check according to WRC code. Here you can see all the calculations and result that stresses not past the strength requirement. And you can see that we have more than 100% here. So our model didn't pass the strength requirement. For example, we can increase the length of this pipe, and to increase the flexibility, run analysis again. Let me check the results. And now you can see that nozzle loads pass the strength requirement. So now our model can work perfectly. We consider only the local flexibility of the vessel shell, but also we can take into account the global flexibility. StarProf allows to do this using the finite element method, but I will not show it in this presentation. I will just do this using the pipe elements. How to do this? You can add the rigid elements in the flange connection. You don't need to use any C-node or other special elements, just add the rigid elements with the length equal to half of diameter with 0 uniform weight. And also you can consider the thermal expansion. And at this point you can add the cylindrical shell element in minus z direction by 2 meters. This is the diameter and wall thickness. The pressure is the same as on the pipe, and the fluid weight is the same. Actually, this is enough to perform the pipe stress analysis, but if you want to receive the loads on the foundation of the vessel, or you want to apply the seismic load, wind load, in this case you need to add the upper part of the vessel. Let me do this. I will just copy this element in this point like this, and you can apply the cap here. So we have our vessel. We can run analysis, and also we need to remove this checkbox. Okay, so now we can run analysis, and we can check deformed shape. Like this. So now StarProf take into account the local flexibility of the nozzle and global flexibility. To demonstrate this, I will add anchor at this point, run analysis again. And now you will see the global flexibility of the vessel. As you can see, the vessel has some displacements in horizontal direction. And also here we have local flexibility. For example, we can remove local flexibility. And in this case, you will see the effect of the global flexibility of the vessel. Here you can see that deformations of the vessel is much greater. Okay, so now I will undo my changes. Okay. Now how to define the pump element. Let me show this. You can remove the anchors and define the pump element here. The shaft axis will be in Y direction. Let me choose the pump center coordinate from the node will be 273 millimeters, and suction node will be 6, and it will be end node. Okay, so now we have pump element. You can copy it in this node too, but if we don't have the second part of the piping system, StarProf will tell you that this factor should be only 1. You can't use the 2 factor according to API 610 code. Let me check here. It is okay. Now 2. Okay. So now we can run analysis. And we can check equipment load. Here you can see the loads on the pump element, but it doesn't use the special appendix of API 610 code that allows you to use up to 2 times greater value of allowable loads. But to do this, you need to define the other part of the piping system after the pump. So how to do this? Let me add the node. I will insert the independent node from the node number 6. It will be into 0.273 millimeters and 0.3 300 millimeters in upper direction. Okay, here. And here I will put the second node. Okay. Now I can define the piping. I will just copy this piping. To save the time and add pipe element here. Okay, so now we have a second piping, and now I will connect the pump to this node. It will be node 13. It will be top nozzle, and now we can use the factor 2 for table nozzle loadings. Okay, and this pump I will specify the node 14. It will be top node. This will be end node. And the factor 2. Okay, so now we have to add some piping after the pump. Let me add, for example, 4-meter pipe and vertical pipe, something like this. It is just for demonstration. It is not real system, just to demonstrate you how to do this. Okay, so I'm finished. Now we can run analysis. And now we can check the pump loads. Now you can see the pump load and allowable load. This is discharge nozzle load and allowable load. You can move your mouse over any cell and see how this value was calculated according to API code. So this nozzle didn't pass the strength requirement, and we need optimization of the piping system. I don't know, maybe, for example, we can increase the length of this pipe. So let me define this node as base node. So now we can change its length and length of this node, this pipe, and this pipe. Something like this. Let me check the results. Okay, so now we don't have any problem with pump system. It is not very accurate optimization. So in real system, you can create a more beautiful system, maybe not so tall pipes, but for demonstration, it is okay. So now we don't have any problem with pump loads. And also, let me demonstrate you how to define the stress intensification factors according to ASME B31J. I will just switch on this option and run analysis. Now, the T stress intensification factors are calculated according to ASME B31J, and also StarProf add the additional nodes. Let me show you. You don't see that nodes, it's hidden. You don't see them, but StarProf add the additional node here, and define the increased thickness of the pipe if the T has the greater thickness than connected pipes. And also it defines the additional nodes at this point and at this point, and consider the flexibilities of a run element at this point and flexibilities at this point of the branch of the pipe. All this is done automatically. You don't need to use any side software, just check this checkbox. And all the T's automatically modeled using the ASME B31J. So now we can switch it off. Now let me show you how to define the tank element. So let me add some additional node to the vessel. I will define the pipe. Something like this in X direction. For example, it will be 30 meters, like this. Add the small additional pipe in Y direction, -1 meter, for example. And here you can copy the bend element, like this. You can define the supports. For example, every 2 meters, I will place resting support. Oh, sorry. Every 2 meters, resting support. Okay. So now here we can define the tank element. I will choose the tank nozzle. Specify the material, for example, the temperature. I don't know which one to choose. For example, 60 degrees, the radius of the tank, wall thickness. Oh no, it's distance from the bottom. the wall thickness, the diameter, and filling height, it will be 5 meters. The density of product will be water. And also we can define the tank settlement, but I will not do this because I want to see the deformations of our piping system. Also, you can define the flexibilities according to API 650, and you can check the loads according to API 650 finite element method, or you can define allowable loads manually. I will choose API 650. Okay, so now we have the tank. StarProf will automatically consider the bulging effect of the tank when you fill the tank with the fluid. The nozzle will rotate and move in a radial direction. And also StarProf take into account the thermal expansion of the tank, and also it can take into account the settlement. And it check allowable loads according to API code, or also you can use the finite element method to do this. It will be more accurate. And StarProf also calculate the flexibility of this nozzle. So now we can run analysis and see. I will just show you the deformation shape of this piping system. It will be like this. And also you can check the nozzle and equipment loads. As you can see, we have a problem with the nozzle of the tank. I will not show you how to improve this system right now because I already have no time for this. I see in Q&A box somebody asked how to define several temperatures. Let me show you. You can define unlimited number of temperatures, pressures in StarProf. You just open the operational mode editor like this and just define, for example, 2 additional operational modes. I will call it pump 1, pump 2, for example. Click OK. And now I choose the current operational mode. It will be, for example, pump 1. Now I choose, for example, I can add the valve element at this point. For example, it will be for 400 millimeters. I will not perform the flange check for this valve. It's too long. Okay, and add the second valve on the other side. So now I will choose this part of piping system and set the temperature to, for example, 20 degrees and the pressure to 0. And after that, I change the to the second operational mode, pump 2, and select this part of pipe and change the properties of that object. The temperature will be 20 and pressure is 0. Now we can check using the project tree. I will choose the temperature. So you can see the temperatures in pump 2 mode, in pump 1 mode, and in operational mode. Okay, so now we can run analysis. The same way you can define the pressure relief valve, forces, this wind loads and seismic loads, everything you want using the operational mode editor. I will show you how to do this. Let me show you the operational mode. This is the main mode. This is pump 1 working, and pump 2. And now operational mode, both pumps working. I hope you can see the difference in deformed shape. In this case, we have this mode shape, this one, and this one. So we have 3 operational modes. Also, you can define the wind loads, seismic loads. Let me show you quickly how to do this. It's very easy. Just define the accelerations in X, Y, and Z direction. And I will not show you the ice and snow loads. I will show you only wind load. For example, the speed will be 30 meters, occasional standard. I will define the next direction, minus X, next direction plus Y, and next direction minus Y. You can define any number of directions. You can add 8, 9, 10 directions as you wish. So now I open operational mode editor. If I will not check the seismic, you will see the load cases. Here is the load cases without wind and without seismic. Now I add seismic checkbox, and you see the load cases with seismic. I remove this checkbox and use wind. Now you see wind loads, load cases for wind loads. Okay, so now I will check both of them. We have a lot of load cases, and each operational mode has its own number of load cases. Okay, so now I will click OK and run analysis. Oh, sorry, I forget to define the wind shape factor. Let me select all the model and define wind shape factor for all piping system, and run analysis again. Okay, analysis is done. Now the best way to see results is to see the deformed shape. Let me show this. This is operational mode. This is wind loads. We have rigid system, so our wind loads is not so great. You'll see it like this. Okay. And you can see the seismic loads in X direction, Y direction, and Z direction. Okay, and let me show you quickly how to define the buried piping. Let me define the vertical pipe here, minus 1.5 meter, and I select this checkbox. Pipe is, oh sorry, I can't show the buried piping in ASME B31.3. I need to change the code. So at this moment, let me show one more feature. Okay, I will unselect the seismic and wind loads. Let me set some parameters. Okay. So now you can see the natural frequencies of this piping system. This is the first natural frequency, second, third, and others. The masses are placed automatically. You can display mass elements. You don't need to split your piping system manually. Just draw your piping system in the standard way and just run dynamic analysis. It's very easy. All the masses will be placed automatically. And let me uncheck the mess. Okay, so, and now let me quickly show you how to define the buried piping. Let me create new piping system using the ASME B31.3 code. I will just create the simple pipe. For example, 2 meters by X direction. It will be 90 degrees with fluid. Okay, I will put anchor here, and now the pipe goes down by -1 meter and 1.5 meter the next pipe, and it will be buried. Here I define the type, this type of soil. You can choose the soil from database. I will just leave default value. Okay, so this pipe is buried. Now let me define the next pipe by Y direction, for example 30 meters, and put anchor and define bands. First band, and copy this here. Okay, our model is ready. So now let me run analysis. And let me show you the soil supports. Okay, so this is soil supports that StarProf automatically places. You can see the soil surface. Also, you can add, for example, the expansion loop like this, 90 degrees, and choose the elbow element and run analysis again. You can see that the soil supports are placed automatically. You can see deformed shape, stresses in this piping system, and you can change everything. For example, change this leg and anything else. Also, you can define, I will not show this, just will tell you that also you can define this pipe is submerged underwater, and also you can define the soil subsidence to model the landslide, soil subsidence, and some other effects. I will not show this because we already have no time. So I hope you like my presentation, and now I will answer your questions. I already see we have 10 questions. StarProf available for student version. Yes, we have student version, but it is free version, but we can offer it only for university. So if university will sign the contract with us, we will offer the several network licenses of StarProf for free for this university. We have the free trial version for 1 month. You can download it here at the website demo.pasuite.com. Next question. Could you please show us the exchange with Aviva, Everything 3D, and PDMS? It is not so easy to show you this right now, but you can go to our YouTube channel I will show you this just a second. Okay. You can open our YouTube channel. Also, you can find the link to our YouTube channel on our website, passsuite.com, and find there the link to YouTube channel. And here we have the video how to exchange the data between StarProf and PDMS. It is exchanged without using any intermediate file format like PCF or like neutral format, nothing. StarProf works directly with PDMS software and with Everything 3D using the special plugin, and it is for free. If you buy StarProf, you will get this function for free.